what we describe in the JASA paper that's in press. And then the second half will be some new developments. So some of them are methodological and some of them are more on the theoretical side. But to make the talk self-contained, I'll start with the basics. So the setup that we're interested in is a large-scale Bayesian model or random effect model with high dimensions. So both of these setups can be summarized with this mathematical formalism. So it's the usual thing where you have a distribution over X, which is a high-dimensional variable, and we only know it up to normalization constant. A typical, for example, in the Bayesian motivation, that would be the joint density of the unknown quantity X and the known quantity Y divided by the evidence. So computing the evidence would require a high-dimensional integral or a sum over a combinatorial space. So we want some approximations. And today, for this presentation, we're going to focus on approximations based on the law of large numbers. So we want random variables xi's, where if we are interested in any test function of interest, the average converges to, in the Bayesian setup, for example, the conditional expectation given the data. So a very standard setup. The twist will be that we'll change this integer index list of sample by a process, so a continuous time process. So let's specialize a little bit for simplicity to the case where X is in just the Euclidean d-dimensional space. There's some, this can be relaxed, but just to keep things simple, let's stay in that context. The inspiration for this work comes from developments in the field of molecular simulations, where the particle in BPS is an actual molecule that moves around, and several of them are moving and interacting. So we're going to use some of the developments in there and build on it for the more abstract setup that I described in the previous slide. So this Bouncy Particle Sampler algorithm has two particularities compared to algorithms like NCMC that we typically use for this setup. The first one is that we're going to get, as I mentioned, continuous time trajectories. So there are several MCMC methods that are inspired or motivated by a stochastic process indexed by time. But in most cases, for example, when it's a diffusion, this is of course changing in recent developments, but at least in classical setup, at the end of the day, we discretize this process and we end up with something that looks like this. So basically, the state is the same for a certain period, the fixed period, and then jump to another one. What we're going to get instead is a process where the trajectories are simple, so we can actually represent them as a continuous object. So they are going to be piecewise continuous in this talk, in particular. And there are practical utilities for this, these type of structure. For example, if you have a constrained state space, then and you can compute the intersection of these lines, of these trajectories with the boundaries, it makes some of the derivation simple and simpler, and also the algorithms in practice. Also, if you have a complex test function, you can exploit numerical integration on these paths. So I'll come back on these a little bit after. And the second particularity is that it's a non-reversible rejection-free dynamics, meaning that so non-reversible in the mathematical sense, and rejection-free in the sense that each piece of computation will change the configuration of the state space. And the consequences of these characteristics is that from our empirical and theoretical results, this class of algorithms seems to be promising alternatives to Metropolis-Hastings algorithms in certain contexts. So I'll try to describe what are these cases that we've identified where this seems most promising. And also these features, the non-reversibility and the continuous time trajectories yields an interesting theoretical analysis of the properties of the algorithm. So the outline for today is, so I'm going to start with some establishing some connection with previous work. I'll describe the basic methods, try to convince you that it's something that's practical and can be used in the concrete scenarios of interest. I'll show you how you can exploit the sparse graphical model structure if it's available. And then I'm going to talk about some recent work. So one of them is cases where the objective function is only known as a black box, meaning you can only compute the gradient at any given point. What can you do in this context, and how you can connect the BPS in this setting with discrete time algorithms. Also some new work on finer theoretical analysis. So I'll give an outline of some recent geometric ergodicity result and consequences in central limit theory. And if I have time, I'll talk a bit more about the empirical evaluation of these algorithms. Okay, so just make sure. So I started at 2:15, right? Okay, perfect. So I have 45. Okay. So first connection I want to draw, which I'm sure lots of people here have in mind already, is with HMC. And with HMC Hamiltonian Monte Carlo, we augment the state space with a velocity or auxiliary variable v, and then we would like ideally, and in some specific case, for example, truncated normal can simulate the Hamiltonian dynamics that's associated with the target distribution. But if we're not in a normal distribution case, we have to discretize these Hamiltonian flows, and this means that we use leapfrog integrator. And at the end of the day, in order to preserve the right distribution invariant, we need to accept or reject to correct for numerical errors. And this makes, at least in the some of the ways to do this correction makes the process reversible. But more importantly, there's a practical difficulty, which is to pick the grid size of this discretization. In particular, if it's, so we would like naively to pick it as large as possible to make the computation faster for these trajectories. But if it's larger than some critical value, performance become qualitatively to degrade. So these tuning parameters are hard, and they might be dependent on the region of the state space that you are at. So this is a practical limitation that practitioners of HMC know very well. The work that I'm going to talk about is connected with many other things. So the first two I want to mention is the work of Birkens and Roberts, who are here on the scaling limits of lifted MH. And from that came out methodological contribution, the zigzag samplers, which I can talk a little bit at the end how the BPS differ from the zigzag sampler. Today I'm going to use two other connections more closely. One of them is the reflective slice sampling of Neal 2003. So there is the naive version that use slicing and coordinate-wise, but there's a more advanced version which uses the gradient that Neal called the reflective slice sampling. And I'll talk a little bit about the connection of this algorithm with BPS and its generalization. Another interesting generalization of BPS is piecewise deterministic Markov models. So I'll come back to that a little bit later, but just to give like a seminal reference on that topic is the 1993 book by Davis. And a few other things that are connected in various ways. So there's stochastic Bayards, which is an active field of applied mathematics, where you look at essentially at a version where you sample from a uniform distribution and you bounce on boundaries. The celebrated hit and run that has similar flavor, and a bunch of other things that I'm showing here quickly. So just to establish that this does not come from thin air, that's some developments that arise from borrowing from many different fields. Okay, so let's start by talking about the BPS algorithm. There's a review or an algorithmic description of what it does. in its most basic version. Okay. So as an HMC, I'm going to augment the target distribution with the velocity variable. So I'm going to call this V throughout the talk. And another concept that I'll use that's similar in the HMC from the same physics origin is the energy, which is just the negative log density. Okay. And so this is U, which I'm going to use at several places in the talk. Okay, so now what are we going to do with V? We're going to do something different than HMC. Instead of trying to have these complicated trajectories, the Hamiltonian dynamics, we're going to have simple piecewise linear trajectories, which you can actually represent in a computer. And so we're going to follow this deterministic trajectory for a random time. Okay, the time that we're going to keep going this way is going to be called tau. So these are the bounce time. And once we go for length tau1, there's going to be a deterministic event, a bounce, which you can interpret as a Newtonian bounce on the gradient. So imagine that so tau gives you a certain point. You can evaluate the gradient at this point. That gives you a plane. And imagine that the particle just bounces off that gradient. Okay, so it's a deterministic function of the position, velocity, and the energy. And then we repeat. So we simulate a new waiting time, and then bounce again, and so on. Okay? So this is the basic version of what the BPS is. So that's the algorithm proposed by the physicists, Peterson and DeWitt. And now we want to apply this for Bayesian computation or random effect model and so on. So we have to answer these important questions. So how do we estimate expectations from these constant time trajectories? And more importantly, how do we simulate the collision time, tau1, tau2, and so on, so that we get a law of large number to the right target distribution, the posterior of interest. So I'll go over these two questions. So it turns out this one is easy. This one takes a bit more work. But let's start with this one, which is important in practice. So we get these trajectories, and we're interested in computing the posterior expectation of this function. So recall this was the test function here that I'm interested in. So it's a function that takes the state space, gives me a number, and I want to compute its expectation. Okay, so it turns out what we're going to do is just simply taking a path integral over that line. Okay, so we're going to take this, more precisely, this process that I've simulated, which piecewise linear, apply this test function, and integrate over t, which breaks down as a sum over segments of these line integrals. And that will give me my estimator, such that as the length of the process goes to infinity, I will converge to the expectation of interest. Now, this may seem troublesome because this is an integral, and what I was trying to avoid is taking integral in the first place. But the key point is that this is a univariate integral, so you can either approach it with numerical methods and still have a law of large number and be very efficient, or in simple cases where, for example, tau or phi, the test function, is a moment or a test function, then you can often solve these analytically. So this part is not problematic. The part that's a bit more that needs a bit more work is basically computing these collision times. So what we have is that in order to have a law of large number, we have some constraints on the law of these bounce time tau. Okay, and given the dynamics and bounce that I gave you, some conditions that are sufficient is to basically have these bounce time tau to satisfy this integral equation. So let me go over this to show that this is not as hard as it looks. Let's look at, in a specific case, if we're sampling from a normal distribution, which is not what we want to do, but gives us some easy intuition. So let's look at what happens along this segment here. So we're just bounced the first time, and we want to find the time that we're going to follow this trajectory. And so what we're going to do is we're going to look at the gradient of my energy along that line. So this is normal, so this is just a linear function. We're going to truncate it so that it's positive. So we get that piecewise linear function in one dimension. So here, again, so this is time, and this is the value of this function I'm plotting. I'm going to sample a uniform number, okay? And so this means that the left-hand side of this equation is just an exponential. And I'm going to ask how far can I go, the minimum I can go, such that this integral is equal to that this exponential random number that I just sampled, okay? So that will give me the first time of my collision. So you see log v is the minus log v is the area under the curve here. So this at least should give you some rough idea of like the type of computation that we need to make. Okay, so this is for the bounce time. So at first, although this is not too hard to explain, it still seems cumbersome. And in some cases, it may be too hard to solve quickly. But we have at least an inventory of methods that are applicable in cases that are more interesting than just normal distribution. So I'll talk about quickly two methods that you can use to compute to solve these integral equations in problems of interest. So the first one is we're going to assume that, let's say for simplicity, that we have a log concave density. So it's a little bit more general than that. But so what this means is that if we look at this integral that we had here, the gradient here will be essentially, so there will be a period, a first segment, which might be 0, where this max will be 0. And then after this segment, this function will be positive, and under reasonable assumption will be also have a derivative. So we can use basically the fundamental theorem of calculus and say that this integral equation is actually just solving two numerical optimization problems, but univariate. The first one being to find the minimum of my energy along the ray that I'm looking, and I'm going to call tau star this point. Okay, so this corresponds to the point here where my directional derivative starts to grow. And then I'm going to say, along this segment, so I can just apply the fundamental theorem of calculus. So all I'm doing is basically trying to find I'm going to look at my exponential as a height in the original energy picture. And I'm going to ask how far can I go such that the value of the energy at this new collision point minus the energy at the local minimum is equal to that exponential. Okay, so this is again something that I can either find in closed form or use a very fast numerical routine. So this is for, that covers also, for example, quasi-concave or convex densities where the contour lines are convex sets. But of course, we would like to go further than this. So we're going to look as well as a way to compose these optimization problems to solve more interesting problems. The second part is the second method to compose these methods is looking at it from a Poisson process interpretation. So we're going to denote chi of t to be a non-negative intensity function. And basically, so the number of points in an interval is Poisson distributed with the mean given by the area under that function chi. And in this case, the bounce time, which I had in the previous slide, can actually be interpreted as the first arrival in an inhomogeneous Poisson process with the rate given by basically what was inside this integral that I had earlier. Okay, so this is just from basic properties of Poisson processes that I'm going to simply build chi by evaluating lambda along that line, lambda being the max of the directional derivative truncated at 0. Okay? So this, of course, means that it's not a result in itself, but what it says is that we can leverage result from simulation of inhomogeneous Poisson processes to help us with that simulation. So an example of this is we can use thinning. So if we have an upper bound on the intensity, lambda bar, then we can simulate a Poisson process with the intensity given by the bound lambda bar. Typically, we'd pick something simple, maybe like linear or stepwise or so on. And then for each point, we keep the point with probability given by the ratio of the bound by the original intensity. Okay? What's interesting here is that even if the point is rejected, instead of not moving, we move at least as far as that rejected point. So in this sense, even using these tricks, we're still in that rejection-free context that each piece of computation brings a different sample. For example, you can use this to look at exponential families. So if you have an exponential family with a Gaussian prior on the natural parameter, then what we're going to do is look at each of these terms separately, okay, and construct an algorithm for collision time as if there were only this part, and then combine them using superposition. Okay, so Poisson superposition. So the more precisely, if we look at the bound of this for this whole object, it will be basically a max of a sum. So what we're going to do is invert the order of the sum and the max. So we get a bound where each of these takes the form of my original problem as if there were only one term here. And so now it turns out that each of these are convex. For complex problem, it's not the case. You might have a non-convex function, but each term might be convex. And in this case, we can still use the same strategy, meaning we compute the first arrival for each of these terms, and then we pick the smallest one, and we say this is the first proposed point, and then accept reject using the bound that I gave in the previous, the ratio that I gave in the previous slide. So this will be the accept reject. So this gives an example of how this would be used for some slightly more interesting problem. Where it gets really interesting, though, is when you can infuse additional structure to the sampler. So, namely, I'm going to look if you have a sparse graphical model for your target distribution. So let me give some quick background on factor graphs. Let's assume that our target distribution can be written as a product indexed by f, where each of these is a function that depends on a subset of the variables, okay? And we can draw a graph where the squares are each of these factors, these functions, which we connect, and the circles are variables, and we connect the factor to the variable that the factor depends on. Okay, so it's a very straightforward representation, but useful to visualize what will happen in the next slide. Now, the idea behind the local VPS is we're going to do something similar to what we did in the exponential family example I just gave, but we're going to change two things, okay? So as before, we're going to define one Poisson process for each factor, okay? But the difference is that we're going to always accept the first event that comes, but instead of bouncing with respect to the full target distribution, or the gradient of the full target distribution, we're going to bounce only with the factor that caused the collision. And it's easy to show that these two, they balance each other, so you still have an invariant, you still target the right distribution, but the algorithm has very different properties. So just to give you some intuition, what are these important differences? Let's look at a simple example where we have some sort of HMM type structure on the latent variables. So I'm going to draw here a picture where the time evolution of the algorithm is from top to bottom, and I'm showing the 4 coordinates, the 4 dimension as time goes. X1 up to X4 is the initial position, and now we're going to simulate, as I promised, one first arrival time for, or a proposed first arrival for each of these factors. The smallest win. So this is the first collision. And as I mentioned, this collision here is just changing these 2 coordinates, because you can think about it as we're bouncing on only the subspace created by this, the gradient of this single factor that depends on these 2 variables. So at this point, we need to update the collision time because the variables have changed, the velocities have changed. So we need to, so this is the second square here. The second collision time is, so it's updated for this variable, But for this variable, the key thing to notice is that we do not need to recompute it because the variable involved in the computation of that waiting time have not changed. So this is a simple observation, but in practice, if your graph is very big, this means that you could have huge savings in the sense that even though the graph could be arbitrarily large, you only pay the collision of order 1. You only pay the computational cost of the order of the neighborhood, essentially, or the extended neighborhood in order to do that step. So it's a bit of a flavor of a Gibbs algorithm, but the difference with a Gibbs algorithm is that the other variables continue to implicitly evolve just by keeping their straight line trajectory. So in practice, there's big savings if the graphical model has this structure. Okay, so sorry if I went a bit quick on this, but I just wanted to get a bit to the new stuff. Any questions so far? Okay. So let's talk a little bit about kind of where this method fits in the spectrum and motivation for the current work we're doing. Okay. So here I'm trying to show a little bit what's the range of assumptions that are made in roughly in Monte Carlo methods. So often there's a trade-off if you make very few assumptions, like just being able to generate data sets versus being able to compute the gradient of the log density. Often you'll have the reverse trade-off where things will become more efficient if you make more assumptions, of course. So for example, HMC would sit here and can be implemented fairly automatically in the sense that, for example, when you use STAN, you can just write in a probabilistic programming language what is your distribution, and you get a sampler automatically. And so you cannot see, but there's a box here that shows sort of these guys are the realm of probabilistic programming currently. And Bouncy Particle Sampler sits just a little bit outside because it has this additional assumption that you need to compute these collision times. And in certain cases, for certain restricted family of model, we can automate this because we know at least how to sum things and how to deal with convex. So we could use ideas from the discipline convex programming, for example, to have some type of probabilistic programming, but it's more limited than what you can do here. So what we're interested in is looking at if there would be an analog of the Bouncy Particle Sampler that could accommodate only this more restrictive assumption of pointwise evaluation of the density of the gradient, pointwise evaluation of the gradient. But there are already methods doing this, so what we really care about is whether we can do some sort of technology transfer. Some of the ideas from the Bouncy Particle Sampler, can we import them in cases where we have less structure? So just to give you some concrete example of the sort of things that we would like to be able to apply to the other setups. So to the black box setup. So there has been in 2016, 2017, several different notions of bounces that have been proposed in the literature that generalize or differ from that Newtonian bounce that I described, okay? So there's one coming from, okay, so I'm trying to basically describe them with these pictures, and this picture is basically, this square is like the gradient, okay? And I'm looking at it from above here, and I'm looking at it from sort of as if the gradient is this line, okay? So if the standard bounce, if I'm looking at it from above, and you have this particle that's bouncing, from above, it looks like it's following a straight line, okay? And if I'm looking from like under the table, it looks like this, right? The angle here is the same as the angle here, okay? So there are some other notion of bounce that have been proposed. The one proposed by Arnaud and all these physicists is that you randomize everything, basically. Okay, so there's this distribution can be arbitrary. This one is constrained, and you can actually show that it's basically a Rayleigh distribution that you have to pick for in the unconstrained case. Then there's this work by Wu and Robert on generalized VPS, where the angle is still Newtonian, but the direction, when you look above, is randomized. Okay, the motivation being to, so I'll talk about the motivation later. And then a last one is the other way around, where you keep the same direction if you look from above, and you randomize the angle of attack after exiting. And so it's interesting because these have pretty complex trade-offs, and we would like to be able to say, okay, can we apply these kind of these algorithms to a black box scenario where we only are able to evaluate the gradient. So I'm going to introduce some notation for a generalized bounce. So I'm going to write these generalized bounce in terms of transition kernel that depends on the point where you bounce, and it's some distribution of the new velocity. So for example, it's a point mass at what we denote Rxv, so just the velocity after reflection for standard BPS. And for these other examples, we get some non-degenerate distributions, okay? So basically by making this generalization, instead of calling BPS, it might be more fair to say that we enter the realm of piecewise deterministic Markov processes, where basically you say there's some deterministic behavior, which in this case happens to be straight line, and then there's a transition kernel, that is the jump, which just changed the velocity, and these happen at some intensity, which we're going to keep the same as the BPS for today. So if you keep the same rate at which things occur, and the piecewise linear dynamics, you get that basically there's sufficient conditions for invariance, that if you want your distribution on bounces to be correct, and people know about this, physicists have known that for a while, you need to basically satisfy this, what is, essentially you can think about it as a skew-symmetric equation, where basically dV is the invariant distribution on V, so in some cases it's multivariate normal, sometimes it's uniform on a sphere, and so on. And you see it looks like a balanced equation, but skewed by this minus velocity here, okay? So this is known. Now, let's come back to that situation I was talking. So we have this, I want to do this technology transfer where in the continuous time realm, we have all these ideas, so these different bounces, and we only know to do black box if we are in the discrete time. So can we apply some of these generalized bounce to a discrete time algorithm, basically, where you don't need to compute collision time? And the answer is yes, and the inspiration for that came from Radford-Neal's reflection sampling algorithm. So I'm going to start with this. I'm going to write Radford-Neal's reflective sampling algorithm first in a more abstract fashion. Okay, so as in Radford-Neal's algorithm, I'm going to sample a slice variable u, which is uniform between 0 and the density at the current point. Okay, and now I'm going to look at if I follow the dynamics for a fixed time step following v, am I still in the slice? If I am still in the slice, then I just keep that point. If I'm not in the slice, I'm going to sample from some distribution that will be my bounce. Okay, basically Radford-Niels algorithm is some type of bounds here, a deterministic function. We're going to ask, can we have some randomization in that object? Okay, so that's what was interesting us. And what we found is that yes, you can use something more general also in the discrete setup. And it turns out that the sufficient condition for this bounds in the discrete setting, the black box setting, to in order to have targeting the right distribution is very similar to the skew-symmetric one that I showed for the continuous time. But instead, what we have is, instead of having lambda, which remember was the intensity of the bounds, we have this indicator that we're still in the slice. And if we follow the trajectory, and here we have the whether we're in the slice if we follow the time reversal of the trajectory. So it's interesting that there is this nice connection, which intrigued us quite a bit. So before going further, so first I want to show that indeed Radford-Niels algorithm does follow this framework. So I'll show you what this Q looks like in the case of reflexive sampling algorithm. I'll skip the proof that it satisfies the equation, but it's easy. Okay, so just basically, so what is reflective slice sampling more precisely? Let's pick the discretization to be 1. So we follow the velocity for time step 1. It's this complicated object where we, so let's say that we, it's really too bad that the colors don't show, but basically, so there's, okay, so there's some, here is the current point. The current, this is the shape of the density line. And this line here is if you follow the current dynamics for one time step, and you don't show it, but you're outside of the slice, okay? And what this kernel will be basically a sum of two things. So you first ask the question, if I follow the dynamics, but instead I first take a bounce, so rather instead of follow the dynamics, I first do a bounce, and I reverse time, and I do, and I'm still in the slice. If this is the case, then do a bounce. So it's a bit confusing. So red is what you do if this pointed line is outside of the slice. So both of these are outside the slice, so you can do the bounce. Intuitively, because if you reverse time, then you would do the same thing. And then if this is not the case, so you don't see it, but here I have basically, if you have what we call a potato, so we have like some sort of weird thing here where like you're outside of the slice here, you're in the slice here, then you just flip the velocity. This is to, again, make sure that intuitively if you reverse time, you're still doing the same thing. So essentially, Radford-Niels has this idea, very nice idea, and now we're now aware of like a formal proof of that idea is pi invariant in the literature. You have to trust Niels. So with this as a special case, you get an easy to derive proof that this kernel here with some pain, you can show it satisfies this. So it's pi invariant. But of course, where it becomes more interesting is that it says you could use indeed all sort of randomized Qs as well to replace Radford-Niels operators. So I'll skip this. So it begs the question also, since we have these two similar equations, what is the relationship between these twos? And one thing we looked at is in the special case where we pick exactly Radford-Niels algorithm. So Q in this case is what I just showed you. And you look at what happened when the step size goes to 0. What you get is basically these potato scales disappear. So as the gradient, as the discretization goes to 0, and you get weak convergence to the BPS algorithm. So this more complicated Radford-Niels algorithm converges to that simpler continuous time BPS algorithm. And so this is, I just saw this morning that this seems to be related to Chris Sherlock's talk on Thursday, so I'm excited to see if it's a different collection of algorithm converging to the BPS or if it's the same one. But also what's interesting with these is that these discrete time PDMPs are still non-reversible. So you get a collection of non-reversible discrete time black box algorithm that all preserve the right target distribution and converge to these PDMPs. So it's some sort of the discrete-time PDMPs, if you want. So I think I won't have time to go into that bit. So, so very roughly, so we looked at, so we already had some results showing that the BPS at the law of large number. We wanted to look at under what condition we would have a central limit theory and via uniform ergodicity. Essentially, we found, as in other cases like Langevin or HMC, that one of the key things to look at is what are the tail assumptions of the target distribution. So there are several regimes of interest. So if the tails are like an exponential distribution and if the tails are between an exponential and a Gaussian, then under reasonable convergence conditions, we have a central limit theorem. Where it becomes more interesting is if the tails are lighter than Gaussian or if the tails are heavier than exponential. And these intuitively make sense. So if the tails are very thick, then the gradient gets very, very small. And if you go very far and you have a method that's based on the gradient, it could get lost. And this is known for Langevin and HMC. For the other situation, if you have something that's for example, think about a Gaussian, but instead of having a polynomial of second degree, a higher polynomial, then the gradient will become very important, very high magnitude, and dominate the refreshment, and you're going to get other types of problems. So we add a geometric ergodicity in the regime where Langevin works. The question was whether we could get result in the cases, for example, where tails are lighter than Gaussian. And for BPS itself, we don't know, but it turns out that if we make a small modification to BPS, which is to increase the rate at which refreshment occur, then we can get geometric ergodicity. So it's a nice situation where the theory actually motivated a methodological development that seems to have a modest impact in practice. So sorry, I had to skip some slides, so I didn't really describe what refreshment is, but in the question I can talk a little bit more about these results. Okay, so maybe I'll just end here not to go over time. So one thing, so continuing on this this stream of geometric ergodicity, so we're looking currently at what happens under heavy tail, and again we have a situation where we cannot make progress on the BPS itself, but we found a methodological change that that allow us to cover heavy tail distribution as well under a central limit theorem. So yeah, sorry for rush talk. Thank you.
So we've got 2 or 3 minutes for questions. Gareth?
Yeah, it's really nice that you've got CLT in the light tail case for the reasons that you pointed out.
Yeah.
But one thing that is always a problem with these kind of methods, as you know, is that the computing cost for the light tail case, especially when you're using things like thin Poisson processes, is very expensive in the tail. So do you have any results about computing time or expected computing time for those cases?
So these, okay, so I glanced over these really quickly, but and the computing cost will be especially large, I would add, if you have an initialization that's far in the tail. So we found at first we actually had some problem differentiating the performance of the algorithm if you're in the stationary regime. For test function, reasonable test function, everything seems to be not going into the pathology that you would go in you could expect. But indeed, if you go very far in the tail, in practice, yeah, you get a lot of collision on small interval. And so this plot that I didn't describe is basically exploring this a little bit, where we, so the blue lines is the version of BPS that doesn't use this norm-dependent refreshment, and the red one is the one that does use this norm-dependent refreshment. And so we look at, further and further initialization in log scale. And this is for a generalized Gaussian where the degree of the polynomial is one more than a Gaussian distribution. And we saw that there was so basically we want these curves to go down as quick as possible. So this modification creates a small advantage. It's nothing to write home about, but at least it's encouraging that it's still expensive to get off the tail, but there's a small gain. Now the interesting thing is that this choice of norm-dependent refreshment was mostly motivated by the statistical analysis. So it could be that by picking some more intelligent function for the adaptive refreshment, we can get some gain. I don't know if it will be a game changer, but at least it seems that it could help. Fixed refreshment.
Well, my question was really related, but it was just: do you have some obvious intuition for why, in the light-tailed case, you're going to want to refresh more often than the tails? Or?
So it's so very roughly, basically, you can there will be two types of events that are always present. So either refreshment event or this collision event, and the fraction of the event that will be bounce will be will dominate the other one. And I don't have a great intuition why, but it's basically you can get stuck on a shell, even though the shell is too far. By just following the bounce, you can get stuck following this high-dimensional shell. And if you're very far, you would want to go straight toward the origin, but the dimensionality of this direction is actually small compared to that high-dimensional shell. So you want to refresh often to have a chance to go towards that center. But if you have, the gradient is too strong, you don't have these chances often enough. That's, I guess, roughly the intuition.
I think we are going to stop here. Let's thank Alex.
And just a quick piece of advertisement. So there's many of you are interested in SMC methods, and maybe some students haven't heard about that. But there's an SMC workshop in Uppsala that you might be interested. And please ask me if you have any question about that workshop.
Okay, and now we're going to have a coffee break, and we will resume at 3:30.